Hello, and welcome to another episode of Research Goes Live, the podcast by the University of Pannonia that focuses on the research of our doctoral students and discusses their importance and impact on our everyday lives. I am your host, Laszlo Gábor, and today we are joined by Bálint Levente Tarcsay, a doctoral student from the Faculty of Engineering. Welcome.
Welcome. Hello.
So why don't you tell us a little bit more about the main focus of your research?
I mainly focus on data science, I guess, and model-based approaches. It's a real bundle of applied mathematics and some information technology. That is what my main research focus is, but I also branched out to some different topics. I was also interested in sensor placement in systems for fault analysis and fault propagation. So fault propagation paths, how does a fault change and evolve in a system? Like if a fault occurs in point A, how does that propagate in different directions, be it within that system that I'm investigating, or even to different subsystems of one industrial technology, or even just one appliance like a vehicle or something like that.
You mentioned fault detection and fault isolation. Can you tell us a little bit about the difference between the two?
Well, fault detection is the ability to recognize that the process abnormality is present within a system. Like you want something to be at a specified value or work in a specified way, and it doesn't work in that way. And the first thing is that you should be able to detect this. And this sounds like a trivial task, but it's really important to denote that faults are usually small scale, and the time of recognition should be as early as possible. So you don't want faults to be recognized when it's so big that the difference between the normal and the current process operation is so big that you can see, okay, it should be like 20 degrees Celsius in this application. It's right now at 60 degrees. So that anyone can detect that. What people want to really detect and what people really want to see is the ability to differentiate between small changes in a process due to noise, which is always there, of course, measurement noise, the influence of the environment, all of these things. For example, just from the temperature, the ambient temperature where that system is located will also change. So it really depends, is it spring, is it summer, is it winter, what's the temperature around it? This will also influence the temperature of the system itself, so it won't be exactly at 20 degrees Celsius, above, a bit below, it will fluctuate. And you have to be able to tell the difference between, is this fluctuation because of some fault that is right now starting and going to become an even bigger issue, or is it just measurement error, change in operating conditions around it, the ambient temperature changes. So yeah, that's fault detection. And fault isolation is the ability to pinpoint what type of fault was this. So when I've noticed that there is a change in this process, an abnormal change, I have to be able to pinpoint, okay, I have these measured variables, they deviate from their normal expected values by this much and this much. What type of fault caused this deviation? So I have to tell, okay, the temperature changed. Why did it change? Did it change because there was an error in the cooling system? Did it change because the process is overheating? What was the source? So that's fault isolation. There is also a lot of different layers, and we call them, together fault diagnosis. And there's also one step further where we even want to give an approximation of the fault, the measure of the fault, like what kind of fault was this, how big was this fault signal? So the source which caused the process to change, what was its magnitude? So that's another step further.
Got it. So really I could see three steps here. There's fault detection, fault isolation, and then fault diagnosis.
Well, it's called, the last step is called fault identification, and the fault process is called fault diagnosis, which encompasses all of these steps.
Understood. Now, you kind of went into how fault detection works. How reliant is this on sensors, or is there more of a complex process behind it?
Well, in this case, when you have some kind of system you want to supervise, you always have to kind of divide it into elementary blocks. You can have faults in all kinds of system components, in the sensors, as you mentioned, in the actuators, so in all of the things you use to influence the process itself. Like, for example, let's go back for a second to this water boiler or something example where the temperature was the measured variable, which I referenced to. So you also said, okay, I want it to be this high, this temperature. That component which sets it to, okay, this temperature, it should be this temperature, so I should heat it this much and this much. This can also be faulty. The sensors themselves could be faulty. So even if it's at the desired temperature, the sensor may say, okay, it's not at the desired temperature, it's above it, it's below it. That's another source. The system itself can become faulty as well. So for example, in this really simple water boiler example, you can have, always eludes me this word, the stone that forms in water. This kind of sediment that builds up on these heating devices can cause the given heat that you input into the system to not translate into the water itself. So that's also it's a kind of fouling, I guess.
Okay, so that's that would be lime scale.
Yes,
lime scale that forms.
And fouling due to this build-up.
Understood.
That's also another component. So all of these parts can be faulty. The sensor fault detection is a different topic altogether. So we mostly rely on measured data to supervise, okay, this process is right now running at these conditions. And generally what all of these techniques do, for example, model-based techniques do, is they say it runs like this. We have a mathematical model that describes that this system under these conditions, which we input it, if it works well, should run like this. If they don't match up, then clearly something is amiss. And you can basically calculate back based on these differences with what component was faulty. For example, we have different schemes to filter out, was it a sensor fault, was it an actuator fault, was it a change in parameters due to system changes like fouling, as we mentioned previously.
So specifically with what you're researching, where do you feel this sort of technology can be most useful? So is there a specific industry or a few?
Yes, the more expensive the gear or the equipment is in that industry, the more useful it is. So for safety critical systems, it is a must. In those safety critical systems, for example, in the nuclear energy sector or in the chemical sector, chemical industry, it's really crucial to not just have, these intelligence or data or model-based methods, but also a lot of redundant sensors. So they say we have basically this method which can pinpoint faults, but even that is not enough. We're going to install, back to the really simple example I've given, we're going to install 3 temperature sensors.
Right.
2 of them are completely obsolete. Well, they are redundant, but we can check, okay, one is saying it's 20 degrees, the other 2 are saying it's 22, okay, we can vote, this one is faulty. So that's a lot of extra costs, but the more safety critical a system is, the more they make sure, like, okay, we have these database or model-based methods to supervise, and we also have a lot of redundant parts. So I would say the nuclear energy sector, the entirety of the chemical industrial complex, and a really new emerging and interesting field is, self-driving cars or intelligent cars, because in those systems, like when the system becomes faulty, now that's a big issue. And there's also a really integral part of these self-driving cars, which is called fault-tolerant control. So it's basically based on the idea that if a fault is present in this system, the control system of that car that drives itself should be able to mitigate these effects and counteract them and still be able to proceed around normal operating or driving conditions. So that's also a really new, interesting, emerging field.
Well, that's pretty fascinating. And just going back to what you mentioned on there's more costs with redundant systems, but at the same time, it sounds like more costs up front, but over the long term, it's still going to be cheaper by avoiding an accident, or
if you avoid it, of course.
You can.
So it's one of the questions is, can you avoid it even with redundant sensors? And the other is, do you need to place redundancy everywhere? Like there are many components in a system which are, safety critical. There are other components which are not so safety critical, but faults can propagate. So if something goes amiss in a really, unimportant thing like a valve, you may say, no one cares, it doesn't work as good, it gets stuck a bit, it's not so critical. But maybe that valve feeds into a tank, which provides coolant to a reactor, which is, a nuclear reactor, then it's going to become safety critical. So what many industrial agents do is that they place redundant sensors everywhere. That is a major cost. And these sensors aren't just like things, I buy them once and it's done. No, if one of them gets faulty, you have to exchange it. Yeah. Yes, and they also have to be maintained, so it's maintenance costs. It will skyrocket the maintenance costs. And on another note, you can always say, okay, I place 3. What if the other 2 are faulty and the third one is right? So it's still not 100% guarantee.
That sounds like a statistical game on what is the likelihood that 2 would fail and 1 would,
How many should you place there? Yeah.
Right.
That's a whole different topic.
Yeah, this cost needs analysis is a pretty fascinating topic when it comes to these sorts of fields. But in the end, I would assume that it is still cheaper than a major lawsuit for a company.
Generally.
Yeah.
If a fault detection process is not properly implemented, as I said before, you have lots of instances where there's just some process noise and there's an alarm going off. So in many of these industrial places, when a fault is detected, the alarm starts sounding.
Right.
And there are many process operators who have to deal with these alarms and who also have to maintain the technology in a safe state. And when you have like 30 alarms an hour, that's what we call an alarm flood. And in those cases, many operators tend to just say, okay, let's ignore it. Let's just shut it down. I don't care about it. It can blare all at once. It can ring all at once. I'm going to just ignore it. And if a real safety critical alarm is sounded because, okay, something's not going well, they tend to ignore it. Then tend to just be like, okay, it's just another small deviation. We don't care about it. And then real problems can be caused. What I said before, faults propagate. So if a component doesn't work, it will influence the other components and they won't work properly either.
Understood.
And when a fault starts, you have like 50 blaring alarms.
So it's like a domino effect, really.
Yes.
This is similar to, I think, what some of us experience in our automobiles, where the check engine light comes on so often, people will just after a while ignore it until something terrible happens.
And you get stuck in the middle of the road in the night. Yeah,
that's right.
That's one of those cases actually. So I was given this topic, alarm management, risk safety in industrial complexes. And initially I thought about, going into alarm optimization, but I got really fascinated and sidetracked, I guess, by this topic, by fault detection itself. And I decided, okay, I want to do my thesis on this.
This is interesting, and it just raises another question now that you were talking about this, is where is the human component? So in this process, does it have the ability to shut down something on its own? Or is the sole purpose only to inform the human behind the controls that there's a problem and they make the decision?
That's a really good question. The end goal of this whole procedure is to minimize the human component in these scenarios, because especially as I talked about this, usually it works like this. The fault diagnosis system gives the operators an update, okay, this component is not working properly. And the people will have to make their choice, okay, what do we do? Do we shut it down? Do we use another, reserve application equipment that we have one more of from this kind? And in many cases, when you have these really safety critical systems, human operators can make a lot of errors. So it's not about completely eliminating the human component, but it's a really important goal to minimize the options and the instances where, based on human judgment error, something fatal can happen or something really catastrophic. And right now in the industry, The most common method is we have established limits for what the temperature can be, what pressure can be, what this and that can be in a system, for example, in chemical systems. And if it goes above or below the limit, then an alarm will be sounded and the operators will be notified, and they have to make, the response steps, how to mitigate this fault. And that's what they do right now. So it really involves a human component really strongly, but most of these methods aim to also give ways to counteract these faults. So that's the next big step,
Right.
to establish a sort of fault response system. And fault tolerant control is one of these things where there's an automatic control system that can basically say, okay, this is present, but I still want to maintain the process at this operation. Can I do it? If yes, then I will control it and use other process variables to mitigate the fault effects. And if it can be done, then I will have to notify the human operators, because in the end, if a component is faulty or to the extent where it can't work, a machine can change it. So
to put it in very simple terms as well, it almost sounds like it's filtering information.
Yes.
And what is most important for the human to know.
Yes. So most of the times when something happens that can't be resolved by just control actions, humans have to be notified, and we still need human operators to basically do the heavy lifting.
Absolutely. This kind of reminds me of these, every now and then there's this show that I watch, I believe it's on National Geographic, that deals with airplane catastrophes, how they crash.
No,
but so many times, I just find it fascinating. But what you're talking about right now seems to come up a lot about pilot error in the cockpit when there are so many alarms going off at once, and they're not sure what is important and what is not. Fault detection, at least on my part from this conversation, has always seemed like something that was in the background. So it's there, but it's still crucial. How often do you think that we actually encounter fault detection, if not on a daily basis, but fairly routinely?
Well, it depends on what you call fault detection. So in those cases where you see, for example, an old sir, someone going around and saying, okay, does this work? Is it broken?
Right.
You can see that fairly often in most industrial complexes or anywhere else, but a janitor or someone from the maintenance. But these more sophisticated techniques that I'm also kind of trying to develop, like model-based methods and even database methods, these are, kind of in the stadium where they are proven to be useful. They are applied in some industrial settings, but it's not so common in everyday life, because why would you develop a really complex and intricate fault detection system, for example, for a water boiler in your house?
Right.
Just the fault detection would cost more than just changing the entire boiler altogether. So the development, so someone has to work with that, someone has to do measurements, and then they have to use like their applied skills. And we know that when someone has skills like that, and especially IT and engineering skills, that's never cheap. And that's why in everyday life you don't really come across these instances where these techniques are used. The best thing I can really think of right now is that cars usually have all of these detection systems, when you can also see that it's blaring, like something's abnormal, something's not okay. These are not so sophisticated and not so, deep, like it's not a neural network or artificial intelligence, which you hear of, like ChatGPT or all of these really
not quite there yet
things. Everyone is so afraid of, like, oh, it's so sci-fi, but it's really not. And that's a really simple instance I can think of. So like in the cars, when it's just playing, like, okay, this is not good, this is an alarm, it's going off, something's not okay. That's kind of a primitive, I would say more simplistic fault detection scheme that we can see day to day.
Right. You talked a little bit about what your research is designed for. What other applications do you think it could be used for?
I also thought about this before, and most of these techniques, not entirely in this form, but most of, for example, the data science techniques that I use can be used for a multitude of purposes. And one of the things which I think really is similar to fault detection in industrial systems or any system is human health diagnosis. And that's something that these mostly database methods excel at. there are a lot of techniques to identify, like, is this person in risk of this or this or this disease?
Mhm.
And that's one of the applications which I think is kind of similar in some aspects when you think about it, because we also see, okay, this is the parameter of this patient. Like, he has high blood sugar, he has these issues, his cholesterol is not okay. What diseases is he most likely to get? What diseases is he in danger of? So in this instance, the diagnostic framework can be really similar, and you have this statistical model which is used to estimate, okay, people with these characteristics are more prone to get this type of disease or this type of disease. So that's one of the things which I think really a bit corresponds to my research as well, and is just a generally more humane application of these techniques.
It is, and that's fascinating because, as you mentioned, safety critical, so nuclear and chemical.
Yeah.
But what else could be more safety critical than the human body, this biochemical machine that also needs
let's be
fault
fair,
detection?
safety critical means that if something goes wrong, it's going to be a big boom. So if a nuclear plant goes wrong, then that's something everyone will hear about. If someone's health goes wrong, that's a tragedy as well, but it's not safety critical in the sense that if I have high blood sugar, people around me won't just explode because of that. So
I should hope not.
Yes.
That would be a pretty bad case of high blood sugar.
Yes. Yeah.
And that's why we do this show, to clarify these things.
Exactly.
Yes, so now fault detection seems to be this area where you combine information technology and applied mathematics.
Yes.
So are the two dependent on each other in regard to this fault detection, or actually can they be separated?
Oh, that's a difficult question. Well, IT is crucial for most of these applications because whichever method I talked about, you need to gain information, you need to gain data to verify these techniques, to verify, like, okay, is it working well? And for that, you need, of course, data gathering, data information, and data storage, which is IT specific. And most of these algorithms use, they are run on computers. And they are all run on computers. So you can't really, I think, separate these two in this instance, I would say. But applied mathematics, yes. It's a bit of a tricky question because there are many knowledge-based fault detection schemes which don't really use mathematics, applied mathematics in a straightforward sense, but they use like if, then, or logic. So when you have gathered data about the system, like how does it behave, how does it work, and you have, for example, a fault tree established, it will be like an if this case happens, then this case was the root cause, or this will be the cause, or something like that. And you can basically backtrack and say, okay, I see that the temperature is high, I see that the pressure is low, what was the cause? And I can just backtrack on this logic tree to see, and this is not like an explicit equation-oriented something which you learn in math class, like x plus y equals something. It's more like a logic, a Boolean logic, like I would say that's also applied mathematics, but that's kind of like the border. So that's more like a human, more human-oriented fault detection scheme where you use your own knowledge to create this reasoning chart.
And just circling back for a moment, that comment that you made really made me think about what is actually safety critical and what is not, especially when it means compared to human beings. So high blood sugar is not going to cause people to spontaneously combust around us.
We hope so.
Let's really hope not. But one thing that I did think about was this concept of, for example, fighter pilots and NASA as well, when they have biomed sensors on their astronauts to detect if somebody is having a medical emergency or if they're about to pass out, which possibly could cause a big boom if they're no longer in control.
Yes.
Could it be applied to something like that?
Of course.
Wonderful.
Of course. You can basically use this in any instance where you have some measured variable. It can be anything. So it's not really system dependent. It's mostly used in these big industrial systems because that's where the big money is at.
Right.
So that's where it's really critical that everything goes well. But you can also plug biosensors on a human and see like, what is his blood pressure like? What is his heart rate like? And you can have some statistical approach or something like that to say, okay, this is normal, this is abnormal. And if it's abnormal, what was the cause?
Now, where do you see your research leading? So is there going to be something else that you feel that you may want to investigate further?
I really hope it leads to a PhD title, first of all. And the other thing which I have mentioned previously that I'm really interested in is fold propagation. So that's another thing, another subtopic of this whole question that I'm getting more and more interested in. And I haven't been able to dive into it really thoroughly as of yet, but I also would like to include some semblance of it in my PhD thesis, and I would like to explore it a bit further. And I really like this research topic because it introduced me to like so many approaches in just general engineering practice and research practice and applied mathematics, that I feel like there are broad range of topics where I can go from this. So I can also go into things like research design, analysis of systems, and that's what I personally expect from this. If you ask me like, what do I expect will the world gain from this? Mm-hmm. Then I would say that there have been lots of research instances and a lot of publications on this topic. And most of them have shown really good results for analyzing safety critical or even safety non-critical systems. But we have a lot of emerging technologies which really are dangerous to an extent.
Yeah.
For example, one that comes right off the top of my head, which is so popular right now and so important, is the hydrogen-based energy sector. Mm-hmm. And hydrogen in itself is quite a dangerous component because if it mixes with oxygen, it's going to be highly explosive. So especially in these technologies where you have really big risk and there it will be even more safety critical to properly analyze.
Yes, and there has been precedent for it. We think back to the Hindenburg.
Not just that, we have also had a lot of, well, these are, the older ones, but the Texas oil refining fire, the Bhopal incident. So there have been so many instances where improper safety and risk evaluation has led to really serious consequences, and not just in financial aspects, but also in environmental damage and loss of human life.
This was really a great conversation because it has shown me as well, and I'm sure our audience, that this isn't just simply fault detection, but all the other areas of our lives that this can be applied to and can be applied to in the future. Bálint, I'd like to thank you for joining us today on Research Goes Live. This has been very informative, and I know I've definitely learned something from this as well. We'd like to remind our audience to please join us again for our next episode of Research Goes Live. And as always, don't forget to like and subscribe.